All right, have you ever looked at a massive skyscraper or a huge bridge and just wondered, how do they know it's not going to fall down? Well, a huge part of the answer lies in a special language, a language of forces and pressures. And today, we're going to decode that language and pull back the curtain on the amazing units that build our world. You've probably seen this stuff everywhere, right? This alphabet soup of PSI, KSI, and MPa. They're on tire gauges, on building plans, you name it. They can look pretty intimidating, but honestly, they all tell the exact same kind of story. And we're going to break down exactly what that story is. Okay, so before we get into anything else, we have to lock down one absolutely critical idea, the difference between mass and force. It's simple, but it's everything. Just think of it like this. Mass is the amount of stuff something is made of. Force, on the other hand, is the action, the push or the pull on that stuff. If you can get that difference, you're halfway there. So let's kick things off with the hero of the metric system, the Newton. Its definition comes straight from the mind of Sir Isaac Newton himself, from his second law of motion. It's just so elegant, right? It connects mass, acceleration, and force, all into one perfect, fundamental unit. But what does a Newton actually feel like? I mean, that definition is a bit abstract. Well, it's actually tiny. If you just hold a small apple in the palm of your hands, that little bit of downward force it's putting on you from gravity, that's about 1 Newton. It's a really simple way to get a feel for the scale of this super important unit. Okay, so now let's hop over to the US customary system. Here, the big player for force is the pound force. And this is a really key point. Even though we use the word pound for mass, like when we weigh ourselves, when an engineer says pounds, they almost always mean pound force. They're talking about the pull of gravity. Look, the weight of an apple is fine and dandy for a high school physics problem. But what about the force crushing down on a bridge column or the foundation of a skyscraper? Engineers deal with thousands, sometimes millions of newtons or pounds. An apple just doesn't cut it. They needed a better, more efficient way to talk about these gigantic loads. And enter the kilonewton. It's just like how a kilometer is 1,000 meters. A kilonewton is simply 1,000 newtons. It's the metric system is practical, smart shorthand for the kinds of massive forces you see in civil engineering. And this is where the metric system just shines, you know? The beauty is in its simplicity. To get from newtons to kilonewtons, you just move the decimal point. It's clean, it's straightforward, and it makes handling the enormous numbers in big construction projects so much easier. So to give you a real feel for it, 1 single kilonewton is about 220 pounds of force. You know, that's kind of like the weight of a really heavy motorcycle. All of a sudden, when someone says a bridge needs to support 10,000 kilonewtons, it feels a lot more real, doesn't it? Now, not to be outdone, American engineers have their own version of this shorthand, the KIP. And the name itself gives it away. It comes from mashing kilo and pound together. It's a pretty unique American unit, but it does the exact same job as the kilonewton. It's a convenient way to talk about huge forces. And the logic is exactly the same as the kilonewton. 1 kip is, you guessed it, 1,000 pounds of force. When you're looking at a complicated engineering plan, space is tight and clarity is everything. So writing 120 kips is just way more efficient than writing out 120,000 pounds. And to put that into perspective, 1 kip is roughly the same weight as 450 kilograms. That's like a grand piano, or maybe a small horse. You can start to see why it's such a handy unit for talking about the massive loads in building design. So we've got these awesome units for big forces, kilonewtons and kips. But is that all there is to it? Think about it. If I push on your shoulder with the palm of my hand, it's one thing. But what if I use the same force and push with just my thumb? Feels pretty different, right? That brings us to a really critical idea in engineering. And this illustrates the point perfectly. It's not just about how much force you have, it's about how concentrated that force is. A sharp knife cuts because you're focusing all that force onto a tiny, tiny area, creating a huge amount of pressure. And inside the material itself, we call that concentration of force stress. This quote just nails it. Think about snowshoes. How do they work? They spread your body weight out over a much larger area. That reduces the pressure, so you stay on top of the snow instead of sinking in. Engineers are constantly playing this game, managing the relationship between force and area. Okay, so it's time to finally decode that alphabet soup from the beginning. Every single one of these, psi, KISS, MPa, they're all just measuring pressure or stress. And the formula is always the same. It's just some unit of force divided by some unit of area. So KISS isn't some weird magical term. It's just kips per square inch. Simple as that. It's how engineers measure how concentrated a force is. Now listen up, because this right here is probably the most useful shortcut in all of structural engineering. This is what makes the metric system so slick for this kind of work. 1 megapascal happens to be exactly equal to 1 newton of force spread over one single square millimeter. And since pretty much all modern engineering drawings are in millimeters, this makes the math unbelievably clean and easy. It's why MPa is the global standard. And this isn't just theory, this is the real world. These units are like a universal language for how strong a material is. An engineer in Germany can specify a type of steel as 345 MPa, and a builder in Korea knows exactly what that means. There's no confusion. Let's take a look at what that looks like on paper. So here's a table for some common types of structural steel. You can see the strength, what they call yield stress, is listed in both N/mm squared, which we now know is the same thing as megapascals, and in KSI. That number tells an engineer precisely how much stress that steel can handle before it starts to permanently bend out of shape. It's absolutely critical information. So let's just pull this all together in a quick little cheat sheet. A kip is 1,000 pounds, or about 4.5 kilonewtons. 1 newton per square millimeter is 1 megapascal. That's the magic one. And if you need a quick conversion in your head, 1 megapascal is about 0.15 KSI. This is your go-to guide for translating between the two systems. So, the next time you walk across a bridge, or ride an elevator to the top of a skyscraper, or, hey, even just sit down on a chair, take a second. You now understand the hidden language of forces and stresses that's silently holding everything together, all measured in newtons and kips and megapascals. The question is, what are you going to see differently now?